Surface tension is a property of an interface resulting from the fact that molecules on either side of that interface have different cohesive energies. Okay, so for example, if we consider water and air, water molecules like to be surrounded by other water molecules because they're polar molecules, and so they're much happier to be in the bulk. If they're at the interface and they have fewer neighbors, and so they're in an energetically unfavorable state. Okay? So if we call this cohesive energy per unit molecule U, then its energy at the interface is U divided by 2. So the surface tension is basically an expression of this loss of cohesive energy per unit area. Okay? So it's basically going to scale with U over R squared. It's going to go as the area. So we can see that this surface tension has units of energy per area or force per length. Okay? So in terms of numbers, I think it's good to write a few down. So dyne, so I like CGS units. Dyne is the CGS unit, so that's centimeters, grams, seconds. It's a CGS unit for force. Okay, so it's force per length. One dyne, I remember learning this in my first physics class, and it's a good thing, good way to remember what a dyne is. It's the weight of one mosquito. So for those of you who are interested in insects, that's the thing to remember. So basically, a dyne is about the weight of a mosquito. So we see why surface tension is important for these for insects, because over their length scale, which is about a centimeter, there's the surface tension force around, which is 2 orders of magnitude greater than their weight. Right? So it's very hard for insects to cross interfaces, to detach themselves from interfaces. Okay, and so air, water has a particularly high surface tension. Oil's around a third of that. Liquid metals have the highest, around 500. I'll just write a few notes. I'll write a few extra. I'll write a few extra surface tensions here, just for those. Okay, notes on okay, so I tend to use this for surface tension. But as we'll see, there are other tensions. So there are tensions at all interfaces between liquid, gas, liquid, solid, gas, and these we'll denote by gamma. So I use this basically at fluid, gas. Okay, so units. So 1 dyne (1 gram) centimeter. What do you guys use here? Are you guys CGS, MKS, or worse? Which?
The international system. That'll be MKS.
MKS. Okay, yeah. Okay, so that's fine. That's not complete madness. But it's clear that on a centimeter scale, CGS is the way to go. Okay, so this is actually 10 to the minus 5 newtons. Okay, and we see the weight of one mosquito. Okay, and so just to give you some feel for comparison, 1 atmosphere, which is the pressure we get on the surface of the Earth, so is 101 kilopascals, 10 to the 5 newtons per meter squared, equals 10 to the 6 dyne per centimeter squared. Okay, so these forces are small relative to atmospheric pressures, but nevertheless they're dominant on the scale of insects. Okay, so I always say, I use this. Do you guys use this to denote units? Yep. Square? Yep. So the units are dynes per centimeter, or see, if we were using newtons, we'd say millinewtons per meter, but I never like that because it looks like you should cancel the m's. All right? So we're going to stick with CGS. Okay, and so I'll write down a few. So air, water at 20 degrees C, so at room temperature 72. If we put in soap, which is a surfactant, it brings it down by a factor of 2. So the most powerful surfactant can bring down surface tension of air water to around 20. And if we have, it's also a function of temperature. We'll see why in a moment. If we go up to 100 degrees, it comes down to around 58. I mean, think about it this way. If you heat up a fluid enough, then the molecules actually are happy to pass from the liquid phase to the vapor phase. So it makes sense that the surface tension is going down or even vanishing. Okay, if we have air, ethanol, it's around 23. Now oil, water, around 40. So this is olive oil. Silicone oil. So these are basically 3 different groups. And the third, so if you have air, so the largest is air, molten glass, around 500, also liquid metals. So if you ever spilled mercury, you know that it wants to form a little ball and run around. Okay, and so the reason that we have relatively high liquid metals are strongly cohesive, so U here is around 1 electron volt. Here the cohesive energy is associated with van der Waals forces. For oils, and these are much smaller. These are around 1/40th of an electron volt. And here, it's coming from hydrogen bonds. Which are in between the two. Okay, so those are just some numbers to give you an idea, but common. And basically, every fluid you can find has a surface tension between 10 and 500. Right? So any fluid-fluid combination. So we have a sort of sense of, we can get a good sense via scaling arguments, but when these forces are going to be important. Okay, so this is just an aside, because whenever I do anything, I start talking about biology. So so we've seen that surface tension arises because things don't want to be at the interface, and this is also true in a lot of biological systems. So, for example, in schooling fish, they'll move along in a school, but then if a predator comes in, then these fish will go into a ball. And what does a ball do? It minimizes the surface energy. In fact, it compresses into a ball, again, simply because these guys don't want to be at the interface. So I've been sort of thought about how to formulate this in a sensible way, but there's a sort of a psychological surface tension in these creatures, so it's a bit dodgy. But you get the general idea, right? There's a penalty to being at the interface. And it's actually interesting. Not just fear factor of being eaten, but if you have a pack of cyclists, so you want to move from point A to point B, there's an energetic penalty to being at the surface because you're getting all the wind, right? And so there are ways that you can try and formulate these systems, but these are some shapes that you see for starling flocks. So they basically, again, they somehow realize they're at the interface and attracted in. Here's a good video. But it really does seem to behave like a second phase of fluid. And you can imagine designing experiments where you have a long cylinder of fish and looking to see whether it pinched off in a regular way. But it probably wouldn't, and it's probably much more complicated. Okay, that was a bit... Okay, but now, we've just made some arguments about things not wanting to be an interface, but what actually is an interface? Is it... where in fluid dynamics we're dealing with a continuum hypothesis, that is to say we imagine that things are continuous, but we know that this breaks down the continuum hypothesis, so Navier-Stokes equations, the governing equations, break down when you get down to about 10, the scale of 10 molecules. And we're imagining that an interface is a discontinuity, right? So what is it in reality? We know in reality an air-water interface is going to have some roughness on the molecular scale, right? So first thing to note, there is no surface tension between... The surface tension only exists for if there's some difference between the two phases of fluid, so it's not a continuous variation. So, for example, if this is salt water and this is water, there's just you actually get the interface becomes smeared out, and there's no tension between the two, right? But if you have an oil water, then you have distinct phases, and again, there's this energetic penalty to being at the interface. Okay, so again, in reality, the interface is rough on a molecular scale, and it looks somewhat like this. Mathematically, we just say, "Voop, here's the interface," and let's define an interfacial tension, and that provides the boundary conditions for the governing equations. So, but we can estimate what the scale is. So, if we equate the anomalous surface energy. So, we've already argued that the surface tension has units of energy per area. So if we have a bump on the interface with characteristic scale delta, then the associated energy is going to be surface tension times delta squared. And if we equate that with the thermal agitation energy, then you can get a scale of the roughness. Okay? So this roughness goes as kT divided by the surface tension to the square root. So we can see that this is consistent with treating with the continuum hypothesis, where we say that things are continuous down to 10 molecules. Okay, so let's just show you where this breaks down. So we can actually, they've done experiments now where they can actually look at the molecular scale. So here we see thermal fluctuations in an interface. So as you get near the boiling point, the interface becomes rougher and rougher, and eventually the fluid will pass into the vapor phase. Okay, and again, as we saw from that last scaling, the higher the surface tension, the rougher the interface. Okay, so here you can see this is the actual interface, and you can see individual molecules there. And it's not perfectly smooth because we have this agitation energy, which is basically randomly hitting molecules towards the interface, and if we crank up the energy high enough, the molecules actually cross the interface. So here we crank up the agitation energy through the temperature, and we see actually molecules passing from one phase into the other. So this is basically what happens when you reach boiling point in water. The interfacial tension goes down, and water molecules start passing into the gas phase.
Say something again, John. You said the more surface tension.
The surface tension, as the temperature goes up.
The more roughness?
No. The more surface tension, the flatter it'll be. No. It's a balance. Basically, thermal effects can act to overcome surface tension, right? So they'll basically smooth out or roughen up the interface. That's why I just close this down.
Yeah, thermal agitation tends to roughen up, and surface tension to flatten out.
Yeah, surface tension wants to keep things from okay. Okay, there we were. Why can't I? Hold on. Okay, so let's go. Okay, so we see what an interface is. So an interface is really, it's a mathematical abstraction which we can do by virtue of the fact that our theory for fluid mechanics only has to be accurate down to a scale of 10 molecules. So it's basically an idealization of a curved discontinuity in material properties, where in reality it's going to be a smooth transition. Okay, so we've seen that there's an energy associated with an interface. So the simplest possible problems you can solve involving surface tension are these ones. So in fluid mechanics, typically we have to consider surface tension, we have to consider gravity and inertia. And so for example, the motion of a drop or a bubble, its shape is going to be influenced by the hydrostatic pressures and the inertial pressures associated with its dynamics. But in these idealized situations here, you have something static, so U's irrelevant, and surface tension can easily dominate gravity because there's no fluid. Basically, you are simply dealing with surface energies. So in these cases, you can solve for the shapes of the interfaces. Okay, and so these are simply the surfaces which minimize surface area. And by minimizing surface area, they minimize surface energy. So that's what the system wants to do. So this is why these things are of interest to mathematicians. So you'll get a sort of problem which looks like this. Find the minimal surface bound by some curve C, where these are a curve C, and so you can actually compute these. But again, this is a highly idealized situation. Typically in fluid mechanics, you have to worry about other forces. You have to worry about pressure and dynamic forces. But this is how you can rationalize the shape of a film between two rings. So you'll basically get a catenoid when the rings are close, and then at a critical distance it will break because this area is going to be less than that area. Okay? And so you can predict what the breaking point is. And here we see it in slow motion. We can see how it breaks. So you can calculate this critical distance at which it prefers to be two circles than a catenoid. And as it breaks, actually, you see this pinch off and a residual bubble in the middle. Okay, so this is an important concept. Basically, it's energetically costly for there to be an interface. Okay, for there to be a fluid surface. So this is how you can justify the fact that small drops are spherical. So a sphere is the shape which minimizes the surface area for a given volume. I just screwed this up last time. Let's try and get it right this time. But there's actually a lot of physical systems which you can rationalize with this simple picture. So here we have we can get rid of gravity by putting drops into a neutrally buoyant environment. That is to say, density matching the drop in its ambient, and that's basically what we do here. We have a slight stratification, so they're neutrally stable here, but there's basically the typical rho GZ pressure gradient, which you get within a fluid, is eliminated here. So we see that these drops, which are bound by surface tension, take a spherical form. Okay? And this will also be true when you get so small that the hydrostatic pressures you get on the scale of the drop are negligible. So whenever you see a really small drop, it's going to be spherical, right? And that's simply to minimize the surface energy of the system. Okay, and so you can rationalize if we have these drops being placed onto a rigid surface. It turns, as we'll see later, the actual shape depends not only on this tension, but on this tension and this tension. But generally speaking, as things get smaller, they get more spherical, and as the surface tension is higher, they'll get more spherical. Okay? Because the energetic penalty to being anything else is increased. Okay, and again, so you can do the math. You can say, what's the energy of a cylindrical column, and is it greater or less than the surface energy / surface area of a series of spheres, and the spheres is actually lower. So a cylinder will always break off into a series of spherical drops in order to minimize surface energy. Okay, so and when you have fluid fracture, you take any body of water. This is two jets colliding, which gives rise to a sheet, and then tendrils, and then drops. The small drops are always spherical. And something that you've all thought about when you get ready to go out, and you decide whether you want to go for the wet look or the dry look, whether you want to wear hair gel or not. Your hair sticks together. You get the wet look because if you put water on it, right? Your hair sticks together. And this is simply because of the energetic cost. If you cover all of your hairs with water, there's going to be an enormous energetic penalty, right? So the hairs will stick together, as we see here. So these are basically filaments, and we're withdrawing water, and so they're sticking together, and you see them merging. So the water is acting to cause the hairs to adhere. Okay, and so again, there's an energetic penalty to there being an interface. This is why drops, this is why bubbles and films are very fragile, because if they vanish, then you free all this energy up, right? So you basically pop a bubble, and it quickly goes into a drop. It would be it's much happier. It's in a much lower energy state as a drop. Similarly here, so films are. We can release a lot of energy if we pop the film. So despite the fact that they're stabilized by surfactants, it's in a much happier state if we just get rid of all the surface energy. Okay, so let's. So that's something which is sort of central in the course. You know, whenever you're trying to solve surface tension problems, you're trying to find the configuration, the geometry which minimizes the energy within the system. Okay, so we've seen now we can think of. So we think of the surface tension as being an energy per unit area, or equivalently a force per unit length. So this is a different way to look at surface tension. So when we think of fluids, we think of there being a pressure. So any fluid parcel within a bulk, say within a swimming pool, there's a compressive force per unit area, which we call the pressure. Right? Similarly, at an interface, there's a tensile force per unit length. Okay. So it's again tensile rather than compressive, and because it's at the interface, it has units of force per length rather than force per area. Okay, and so if we do have gradients in surface tension, as can arise from chemical gradients. So, for example, if the surface tension is smaller here, then this blob of fluid will be pulled in that direction. So, if you have gradients in surface tension, as can arise through gradients in temperature or chemistry, you can generate surface forces. And we'll do a number of examples of that during the course of the course. Okay, so now let's try and formulate this problem, a little more formally. So now again we've seen surface tension as force per length or energy per area. So we know that if we can get rid of the film, we'll free up all this surface energy. So we pop the film here, and we can ask what the force is on the rod. Okay, so we can write down a surface energy, which is simply the surface tension times the energy left of the rod. So we know that this is going to change as the rod moves to the right. So the force we can get as the rate of change of surface energy with respect to the position of the rod x. Okay, so that tells us that the force acting on the rod is 2 surface tension x. I'll just write this down over here. So soap film, this is a soap film on a rail. So this is length L, this is X. So this moves an amount dx. So the work done Okay, so why is it 2? because the film has two surfaces, right? It's the top and the bottom, right? Okay, so we see then the force is 2 sigma L is the force on the rod.
It's like this bubble is wrapping around the rod, is that?
Yeah, so the rod is, if you zoom in on the rod looks like this, right? It has this interface, and both interfaces have sigma, right? Right? So this is the rod. This is the film.
Okay, the film has a thickness.
Yeah,
Okay,
yeah. Okay. Yeah. So this is yeah. Okay. Yeah. Okay, this is the top and the bottom. Okay, so more generally, if we have an object, say, floating at an interface, okay, so let's say this is air, this is water, then there's everywhere along the contact line, there's a force per unit length of magnitude prescribed by sigma, which is tangent to the surface. Okay, so it's basically acting in that direction there, in this direction here, and then, depending on how good you are at art, you can draw the but it's basically tangent to the surface, right? Is that clear? So it's everywhere. So it's a force per unit length acting on the contact line, everywhere tangent to the interface. Okay? Okay, the contact line is this guy. Contact line. So that's basically the point where the three phases come together. Okay, so that's where the solid, the liquid, and the gas come together. Okay, and so more generally, if we have, say, let's imagine we have an object which is heavy, now relative, so we're imagining that this was quite happy, and it's, say, if we have now something which is heavy relative to water, then we can have a situation like this. Okay, so the contact line is now this guy, and the surface tension is again acting tangent to the surface all along the contact line, but it now has a vertical component. Okay, so it can actually contribute to weight support. Okay. And we'll go through, we're going to generalize Archimedes' principle. So Archimedes' principle treats the statics of floating objects, but it doesn't consider interfacial effects. And on this scale, where surface tension is important, so it has to be modified. Generalized, I should say. So body is heavy relative to water. Okay, so this is, say, H2O again, air again. Then we have some heavy object. So typically you rely on hydrostatic pressures for weight support, but here, so for small objects, surface tension can dominate. Oops. Wait, what? Okay, let me just see what's coming up next. Yeah, so this is how, oh, okay, here's a good one. This one's will also contribute to your intuition. Yeah? What's that? Top one. Yeah, okay, it's just that one we need to turn off, right? Okay. Okay, we'll turn the lights on again for the front board in a second. But so this gives you good intuition. So you can put a string in a soap film, and it's just sitting there quite happily because surface tension's acting in both directions, right? So it's pulling it out, so it's basically sitting there, doesn't know anything. But then if you pop it inside, then suddenly you create this gradient surface tension. We have nothing pulling back, and we have this pulling this direction, so it gets pulled out into a circle. And it turns out if you look at at a soap film from the side, it gets thicker as it goes down. So there's actually an effective stratification. And so these things are like balloons in the atmosphere. They'll basically go to their level of neutral buoyancy.
Oh, because the film runs down to the gravity?
Yeah, yeah.
This circle adjusts a bit up or a bit down.
Yeah, yeah. Okay, and so again, so this is the sort of picture you see, which I drew here, of this heavy thing sitting at the surface of water. So these water-walking creatures their density is greater than that of water, but they deflect the surface basically like this, and so they get a vertical force which supports their weight. And you can do the same thing with a paper clip. So if you can try this at home, but you just take a paper clip and pick it up with a pair of tweezers, and be careful not to get it greasy. Don't touch it with your hands. But if you take it, you can place it, and despite the fact that it's stainless steel, so it's considerably heavier than water, you can place it on the interface and it will float. So again, it's heavier than water, but it floats by virtue of this. So it's basically getting a force per unit length, which is basically twice surface tension, right? Because if it goes, so the maximum force it can get if this interface is vertical is twice the surface tension. So you can basically then calculate the total weight that surface tension can support. But of course, it's only important on these small scales. I think to support the weight of a human, the perimeter of your feet has to be something like 10 kilometers. Okay. Okay. So here's a question: which way does the air go? Wait, I want to pause this. Okay, ready? So you first you have to guess. Okay. So we have a little bubble and a big bubble. Which one's going to grow and which one's going to shrink? If it's a balloon, which way does it go?
You would think that the little one would grow, right?
I just asked the elastic. Sorry, for a balloon.
I would say the little one would grow.
The little one would grow, exactly. Yeah.
The little one would pump air.
Exactly. So that's what you get for a balloon. So that's sort of your intuition, because you'll spend more time looking at balloons than bubbles. But for bubbles, it's the opposite. Is that okay? Okay, so that sits contrary to our intuition, and so whenever we see something that's contrary to our intuition, it indicates that we don't understand it, and so we have to do the math. So did you believe what you saw, Andre, or are you still doubtful?
I just don't understand.
Yeah. Yeah, you sort of, again, one has intuition based on, it's the nice thing about surface tension is sometimes things are a little counterintuitive. Okay, so we're going to rationalize. So basically what we need to do is see how the pressure depends on the radius of the bubble, right? So this, we saw Laplace. This is basically Laplace pressure for a bubble. Okay, so let's imagine an oil drop in water. Those are simply soap films, but so let's do oil and water. So we know there's going to be some pressure inside, which we'll call pressure of the oil. Then we have the pressure in the water. And we know that there's some, let's call this interfacial tension, sigma oil or gamma oil water. And this thing has, this drop has radius r. And we're going to see what happens if its radius changes by an amount dr. Okay, so work. So we know there's going to be mechanical energy and surface energy change. So the mechanical energy is just P dV work. And then we have a change in surface energy. So this is mechanical energy. And this is surface energy. Okay, so we know, so these changes in volume, so they're going to be equal and opposite. So this is going to be 4 pi r squared dr. And change in area is going to be 8 pi r dr. So for mechanical equilibrium, so this variation in energy has to be 0. So this is okay, so this tells us the change in pressure. Delta P equals P naught minus PW equals 2 sigma, so twice the surface tension over the radius. Okay? So the pressure is always higher inside, and there's a jump across the interface which is proportional to the interfacial tension and inversely proportional to the radius. Okay? So that means that the pressure is higher inside small drops. Okay, and so on the basis of this, we can understand all sorts of things that we come across in everyday life, not just our motivational video. So which is louder, beer or champagne? And why is champagne louder? Exactly. There we go. Now we learned something today. Okay, so things to note. So yeah, so these are our basic pictures. We have when we have a drop or a bubble, we have a pressure inside which is higher, and it's higher by an amount proportional to 1 over the radius. Okay? So note, so pressure inside, drop, bubble, by an amount proportional to sigma over r. So smaller bubbles have higher Laplace pressure. So this Laplace pressure, I'm going to say more generally, we're going to define it in terms of the curvature of the interface for a sphere. It's simply going to go like it's simply 2 over r. So, but this we see is why champagne is louder than beer. Okay, so by the way, so there are 2 different ways that you can rationalize why champagne is louder than beer. So what's the path of so I have one of my friends is funded by Moet to design the optimal champagne bubble, because a good champagne bubble should not spiral as it moves. It should move just in a straight line, and it should be very loud. Both things require that it be small. We know from fluid dynamics, as the Reynolds number of a bubble gets larger, it goes from a straight trajectory to a spiral one. And beer bubbles spiral as they go, right?
So you want a less turbulent champagne.
Yeah, you want the perfect. Yeah, you want the bubble moving in a straight line and being as loud as possible. Both things require that the bubbles be small. Okay.
But does that have anything to do with
But
quality taste?
yeah, no, because that's something they designed. That's sort of understood that champagne should be loud, the bubbles should move straight. So they try and basically design for it. But typically, you get bubbles forming on irregularities on the glass surface and so forth. So you can't. So the detail dynamics do depend on the glass you put it in. Okay, so to get an idea, if we have a water drop with something around a micron, then you can actually get a sizable pressure jump, comparable to an atmosphere. So but more typically for a soap film. Oh yeah, so notice that these were soap. So the soap films. Yeah, so we can rationalize this experiment now, right? So the pressure we know is higher inside the smaller bubble. So because when we connect these two, then the fluid is. Oh, sorry. Wait. I just said. Yeah. The pressure is higher in here, so when we connect it, the flow is pushed from the small to the large bubble.
I'm thinking you're really, so in the birthday party balloons, there's more energy than stored. Why it's going to be the other way around?
So there's actually there's elasticity there, right? Yeah. So there's elastic energy. So there's actually a penalty to surface divergence, which there isn't for a clean surface in fluids. So it's that additional energetic cost which changes things.
Oh, I see. For clean surface, the divergence, there's no penalty.
Yeah. We'll actually come into that because surfactants do actually introduce a penalty to surface divergence. But yeah. Okay, so for a soap bubble, which has two surfaces, Right, so a soap bubble actually looks like this, right? We have two surfaces, both with surface tension sigma. So we have P naught plus delta P, P naught. Then you have delta P equals 4 sigma over R. And so that was what we were seeing there. Okay. And so so if we put in some numbers, I don't know if you guys like putting in numbers. I always like putting in numbers. It gives you an idea of what you're actually dealing with. So if we have 5 centimeters, sigma 35 dynes per centimeter, which is what you get for soap, then delta P is on the order of 3 times 10 to the minus 5 atmospheres. Okay, so it's small. For champagne bubbles, so basically you have something on the order of 100 microns, so they're a fraction of a millimeter. Sigma is around 50, so it's water. The surface tension of water is always the highest. You bring it down by putting in anything, alcohol or anything else. But you see that the pop you're hearing is around 1% of an atmosphere. Okay? So we just did this for the simple case of a sphere, but we can define the Laplace pressure more generally in terms of the geometry of the interface. And so we'll be developing that in detail next class. I'll just write down the answer and show you a few more motivational videos. But you get the idea when you have, basically when you cross an interface, there's a jump in pressure, and the jump in pressure is going to be proportional to the surface tension times the local curvature. Okay? So here the local curvature is just 2 divided by R, but we'll write things more generally here. So delta P, so if we just have an interface now with a normal N, let me kill that. Then we can define the, oh no, I just did it backwards, didn't I? That was stupid. So we can define the curvature as the divergence of the normal N. So we have an interface with the tension sigma, and we know, so the pressure, there's going to be higher pressure here than here, and the jump in pressure is going to be proportional. So our Laplace pressure now, the jump in pressure in crossing the interface is sigma times the divergence of N. Okay? So this is the surface divergence, and I'll define what that is precisely, simply because N is only defined on the interface. We can only evaluate its curvature along a surface, so we call this the surface divergence. But not to worry about that. This is basically a geometric factor, a geometric quantity, which depends on the shape of the interface. Okay? Okay, so we're going to develop that from first principles next time when we'll really think the course will really start in some sense. But let me just do a couple more little things here. So this, as we see, whenever the physical effect is important, nature has to worry about it. So here we have here we have a bug expelling fluid, and when the thing is small, it has to come up with an enormous pressure, right? So again, moving fluids around on a small scale, these are problems that nature has dealt with and learned to cope with. So let me just show you. Okay, so we'll see here the indication of Laplace pressure. So this is a soap bubble full of smoke, and he's going to release it, and you'll see the smoke being ejected. Okay, so
And quite high pressure, right?
yeah. So and the pressure gets higher and higher as it goes, right? Because this thing gets smaller, the pressure inside it gets higher and higher. Okay, so you can we can write down what the characteristic speed is. So who knows what a scaling argument is? Who likes scaling arguments? I really like scaling arguments because you can get the answer without doing any work. So let's, if we have this, if we want an estimate of how fast it goes, so what's the exit speed? So that's this experiment here. So we basically have a tube connected to a soap. Okay, and this has characteristic radius r. We have surface tension sigma. Then we have this jet coming out at a speed u. So basically, this curvature pressure is going to give rise to dynamic pressure. You know, the curvature pressure is going to go like 4 sigma over r. And the characteristic dynamic pressure is going to be rho AU squared. So if that's unfamiliar to any of you, that's the pressure you feel when you're driving in your car and you stick your hand out of the car door. You feel a force which is proportional to your speed squared times the density of the air times the area of your hand. So the characteristic pressure is simply rho A squared. Okay, and so this gives you the exit speed of this jet. So again, that's soap. I should put in 50 dynes per centimeter over 0.001, so 10 to the minus 3 grams per cc, and we start with around 3 centimeters. So you get something on the order of a meter per second. Okay, and so another effect which arises from the fact that pressure is higher within small bubbles is sort of coalescence. So if you start with a foam and you have a range of different bubble sizes, then the pressure is going to be higher inside the small ones. So if the air can actually diffuse from the small to the big ones, then you get this you basically get the small ones disappearing at the expense of the large ones, because the gas diffuses from the small one, is forced. I shouldn't say from the small into the large. So this is called Ostwald ripening. So this you can see in shaving cream foam. So here we see, so this is basically a foam. Again, you see small bubbles and big bubbles. Again, within the small bubbles, we know the pressure is higher, and the gas phase can diffuse across the membranes, the interfaces between the two, and so you get the large bubbles growing at the expense of the small bubbles. just as we saw with those two tubes connected, the small one disappeared, the air went into the large one. Here the same thing's happening, but the air is passing through the interfaces. Okay. Okay, so the last thing I'm going to do, I just have. Do we stop 5 minutes early, or what do we do? What do you guys do here traditionally? You go to the hour, or?
No, you go to wherever you need it. You can stop 5 to 10 minutes earlier or
Okay.
10 minutes later, depending on your need.
Okay, I'll try and. We always stop 5 minutes early at MIT. Okay, so I just want to mention. So who's learned about dimensional analysis? It's one of my favorite subjects. Have you learned about it? Because I kind of picked it up on the street. No one ever taught it to me, but it's incredible what you can do with it. And if you'd like to learn more, I like teaching about it. So who's learned it in class? Because engineers normally use it, right? Yeah. And and I don't know why they don't teach it to physicists. But so one, how else? Dimensional analysis. Raise your hands. Two. Fluids. Yeah, you should do it in fluids. Who's been teaching you fluids? So. Right, so the idea here is that, we'll maybe come back to this next time, but I'll throw this idea out there. So we know that the laws of nature cannot depend on the chosen units. These are a human construction, and nature does not care about humans. And so you can, of course, then this being the case, you can always describe nature in terms of dimensionless groups. Okay? So we have to be able to describe a system entirely in terms of dimensionless variables. So one has to identify them for any physical system, and one does this using this so-called Buckingham's theorem. So if you have m physical variables, and if these m physical variables are described in terms of n fundamental units, so the fundamental units in certainly fluid systems are always the same. They're always mass, length, and time. Okay. Sometimes if you have a variable temperature, you can get that in. But typically, if you have an isothermal system, it's mass, length, and time. But we can have all sorts of physical variables. So density, speed, length, viscosity, different geometric factors all come in as physical variables. Okay? If we have a sphere, then there's only one length scale, right? So we have some hope of getting something. So we can identify. So let's imagine we have the translation of a sphere. Then the physical variables, we have the speed, its size. So these are the two, we're going to come to Navier-Stokes next class, but these are the two fluid variables, the viscosity and the density, and then the drag, d. So we can identify 5 physical variables, and these are expressible in terms of 3 fundamental units, mass, length, and time. Okay, so if we have m physical variables and n fundamental units, then there have to be 2 dimensionless groups describing the system. Okay? So if there are 2 dimensionless groups defining the system, one must be expressible in terms of the other. And so this is where the drag law comes from. And so you can basically characterize the system entirely by expressing one dimensionless group in terms of the other. So we can define, there is some freedom in defining the dimensionless groups. For example, we can multiply them, we can divide them, they're still dimensionless, right? So basically it's a matter of choice. But useful ones in this particular case is we want to see how the drag depends on the speed, right? So we can define this drag coefficient. So that's the drag non-dimensionalized by rho u squared, which is our dynamic pressure. we can see how that depends on Reynolds number. So Reynolds number is the relative importance of inertia and viscosity in the system. Okay? So we expect the drag law to change as a function of the Reynolds number, but this dimensional analysis makes clear that the system can be characterized exactly if you can plot a single curve, right, which is the dependence of this on that. Okay? And this is an extremely powerful thing, my favorite example is actually we've noticed here in this particular case there are two dimensionless groups, and so we can characterize a system by expressing one in terms of the other. And in terms of experiments, this is very nice. So again, you just have a single curve, because you could think, well, if you didn't know about this, you could say, okay, well, let's look at the drag law at this density and then at this density, and then so you wouldn't see that the things are all connected, and you can get characterize the whole system in terms of a single relation between two variables. But the best thing about Buckingham's theorem is if you have the case where there's only one dimensionless group, right? What does that mean? If there's only one dimensionless group, then it has to be, that has nothing to depend on, so it must be constant. And there are quite a few systems where this is the case, and they aren't all trivial. So one of them is the explosion of the atom bomb. So when the first bomb was exploded, they published in Time Life magazine pictures of it. And they had a time scale. They say time equals 1 millisecond, time equals 5 milliseconds, and they had the thing growing. So this is a blast cloud. And there's a house in the foreground, or a tree. I can't remember what it was. But anyways, Taylor knew how to do this, G.I. Taylor. And so computed on the back of an envelope the energy in the blast cloud. So it turns out, in that particular case, I can run through that if you like. I'd be happy to. I kind of like the problem. But you basically have one dimensionless group. So the physical variables there are energy of the blast, radius of the cloud in time, and I think the ambient pressure. But in any case, there's one dimensionless group, and so it has to be constant. And so you can, from that, get the scaling of the blast cloud radius as a function of time. I think it goes as t to the 2/3 or t to the 5/3 or something. And so on the basis of these photographs, G.I. Taylor calculated the energy in the blast, and this was supposed to be top secret. So the CIA came by and arrested him in his house in England, and he's going, "What?" So because you can figure it out, it's not that hard. And so he took a while to convince them, but he had just done the calculation, which is literally back of the envelope. I can do it in one slide next class if you like. But anyways, this is a very powerful way of looking at things. So the constant is usually, in these scaling arguments, for some reason the constant is always between 0.1 and 10 in every problem I've ever worked on, right? And so he kind of waved his hands and said it's around 1, and it was like 1.2, so he got it within a factor of 10% or something, which is, you just want to get things within an order of magnitude. That's all you can get from scaling arguments, right? But and in fact, the same scaling argument was used by a friend of mine who's working in Holland, and there was a factory blew up. It was a fireworks factory, and it was a huge explosion. And there were laws against having too much fireworks in one place. And the factory argued that they weren't in violation of the law, but everyone was going, come on, it must be. That was a massive, it really gutted the city center. It's a massive explosion. And so this guy testified in court, and somebody had a video. They were standing on the roof of their house taking videos of their kids playing in the backyard. And you heard this explosion. So you hear the explosion, and then this guy gets knocked over and the camera goes flying from the shock wave of the explosion. And so they knew where his house was. They knew where the factory was that blew up, and so they knew the distance. So they could calculate from the time of this blast cloud hitting him, using the same scaling argument, how much power is in the blast. And so they indicted the company on the basis of this. Good scaling argument, though. I'll show it to you. Okay, but in any case, this is something that comes up again and again in the course, is dimensional analysis, and basically these guys will become your friends. So this is the importance, these are the importance of various physical effects relative to surface tension. So we see surface tension arises in all of these. So if we imagine now a drop, a fluid drop of radius A hitting a bath at a speed u, then there are various forces around. There's the dynamic pressure associated with the motion, so that's rho u squared. And then we have a curvature pressure, which is, again, our curvature pressure is always surface tension times the curvature. And we saw for a sphere, the curvature is proportional to 1 over the sphere radius. So this is basically rho u squared over sigma over A. So this is inertia relative to curvature. So surface tension is oftentimes competing with inertial forces. So, for example, we'll look at a raindrop at the beginning of next class and look to see when it shears, and that's determined by a ratio of the destabilizing inertial pressures coming from the air and the curvature forces, which are trying to maintain the sphericity of the drop. And then we can look at the relative magnitude of the viscous stress, which is basically rho. This is the fluid viscosity times density times mu divided by A is the characteristic viscous stress, and sigma over A is the curvature. So the A's cancel, and this is the capillary number prescribing importance of viscous stresses to curvature stresses. And then the Bond number, we'll end on this one. This is the most important one. This is saying when, in some sense, when surface tension dominates gravity, and we keep saying surface tension is important relative to gravity when things are small. So this note is the ratio of rho GA, which is a characteristic hydrostatic pressure, to a curvature pressure, sigma over A. And so sigma is dominant relative to gravity when this number is small. Okay. So I'll just end on the next slide, which is spelling this out. So if we put a blob of fluid on a substrate, if we just forget about the wettability of the surface and just to imagine we have just a puddle, which can we know that gravity wants it to go into an infinitely thin puddle, but surface tension wants to maintain the sphericity of the drop, right? And so across this drop, this blob of fluid, we have a hydrostatic, the pressure is increasing here due to gravity, so we have a characteristic pressure difference which is around rho GA, which is this, and then, so that's causing the spreading, and then we have surface tension pressures sigma over A resisting it, okay? So the relative magnitudes of these two things determines, so that's to say the Bond number determines whether or not it spreads or it stays together. If the Bond number is very small, the surface tension wins and the thing remains spherical. If the Bond number is very large, then it spreads into a puddle. Okay? And there's a critical length at which there's a crossover. So these two forces, these two pressures are comparable when the Bond number is order 1, and this happens at this critical length. Okay? And this is the so-called capillary length, and know that it's determined entirely by the surface tension, and so that's the density difference. If you have two phases, I'm just assuming that we have water and air, so the density here is 0. But it's determined, it doesn't depend, there's no geometry in it, so it's simply a function of the interface, right, of the chemical properties of the interface, the surface tension and the density. Okay? And so if we have things which are small relative to this capillary length, then surface tension wins, and if you're large relative to the capillary length, then gravity wins. And so we see immediately that surface tension dominates things which are small for air-water interfaces. That's small on the scale of 2 millimeters. So this is the world of insects and microfluidics. Okay, that's good. We'll get down to business next time and start doing a little math. But I hope to see you on Friday.